Okay, so now we're going to talk about dihydroxylation reactions. So di meaning two, and then the hydroxy portion meaning two OH groups. So these are going to be reactions where we put alcohol groups on both of our vinyl carbons. Okay. So taking just a simple alkene like ethylene, if we perform a dihydroxylation reaction, we are adding onto both of these vinyl carbons an OH group. Actually, the first reaction that we're going to be looking at here is this formation of an epoxide. So just this portion here. So these epoxides are something that we also care about. What is an epoxide? Specifically, that is this portion right here. It's a three-membered ring with oxygen as one of those members. Okay, right, we know that three-membered rings don't like to form all that. There's a lot of angle strain there. So we'll see that these compounds, these epoxides, are highly reactive. Nonetheless, we can form an epoxide, a stable epoxide can be formed from an alkene using what's called a peroxy acid. So let's take a look at one of those we'll take a look at what one of those would look like here in a second. But then notice if I take my epoxide and then I just treat it with acid, I will get a diol, but more specifically a trans diol. Okay, so this would be an anti-addition. But let's take a look first at these epoxide formations. I don't really expect you to know the reaction mechanism for this, but it is interesting to look at. One of the things that you'll see about peroxides and peroxy acids in particular is they're really good at inserting oxygens between two atoms that were bound together, right? So here we have this carbon-carbon double bond, this carbon-carbon pi bond. These carbon atoms are already bound to one another. What these peroxy acids do is stick an oxygen in between those two bonded atoms, giving me my epoxide here. Any peroxy acid would do the trick. Those all have this RCO, some of the times it's OOOH or RCO3H. These are generic forms. What does that mean? So, right, we had our carboxylic acid, so RCOOH looked something like this. These are RCOOH. There's a third one. And so let's take a look at what that looks like here. Notice that we have kind of our normal looking carboxylic acid, except for there's an additional oxygen in that chain there. Okay, so these are peroxy acids. Again, they're really good at inserting oxygens between existing bonds. One that you just have to know the name of because the ACS loves is this MCPBA. All right, so if you see a reaction between an alkene and MCPBA, it's forming an epoxide. And then last thing to note about epoxides is that they are syn additions in that those bonds are both pointed in the same direction. Hopefully that makes sense just by virtue of the fact that it's this ring, right? You can't possibly have an anti-addition to an epoxide or where one bond's sticking above and one bond's sticking below, but you've still formed this three-membered ring. It's not going to work like that, right? So an epoxide is both of those bonds are on the same side of that double bond. Okay, and then what happens when we treat our epoxide with water or acid rather? So again, these epoxides, you can think about them as cyclic intermediates. So what's going to happen when we treat it with acid is actually we're going to protonate that epoxide oxygen. So the first step is epoxide oxygen playing the role of a base, grabs that proton. Now we have this protonated oxygen, making it an even better leaving group than it already was from, even having that angle strain and all that good stuff. And so what we're going to see now is the anti-attack from a neighboring water molecule, right? Because we have these cyclic intermediates, what we've seen with all of our cyclic intermediates is they force the nucleophile to attack from the other side. So that will attack there, and we'll be left with Again, that protonated oxonium ion. So then the last step is just deprotonation from a neighboring water. Okay, and again, very important, these are anti-additions. Okay, so you get the diol, but you get like the trans diol. And again, just sort of hammer this home, we've seen these with all these intermediates, all these cyclic intermediates, whether it's our protonated epoxide, the bromonium ion, or the mercurium ion. These cyclic intermediates make it so that you can't have, you can't have syn addition, you can only have the anti-addition of the nucleophile to these intermediates. So now what if you do want a syndiol, right? So diol just meaning that it's two alcohol groups. For that, you can use a different reaction set of reactants. In this case, these types of reactions can be catalyzed by this guy here. This is osmium oxide, okay? Reacting an alkene with osmium oxide, you will get a syn addition of that osmium oxide, where both oxygens are bound to the same side. If you treat that with like a sulfurous acid and water, what you'll get is that'll cleave off that osmium oxide, leaving you with two OH groups that are now on the same side. So this is a syn diol, or there's been a syn addition of those two alcohol groups. Another way that you can, another compound that is used for this is manganese oxide MnO4, so plays a similar role to osmium oxide, except instead of following it up with a sulfurous acid, you go with a base to cleave off that, that intermediate. But the product is the same. You still have that syn diol that's formed. Okay, so now just looking at each of these three reactions that we just learned about, let's create our little cheat sheet here. So mechanism, no. So I don't expect you to know the mechanisms for any of these, other than for this middle one here, again, just knowing that it goes through that cyclic intermediate. That cyclic epoxide intermediate. This was green. So what about regioselective? No, because you don't have to worry about what's the more highly substituted carbon, what's the less highly substituted carbon. That's not going to factor into your decision when you're thinking about forming an epoxide. It's also not going to factor into your decision in either of these cases either. And that's because you're adding OH groups to both sides. Right, so since you're adding the same thing to either vinyl carbon, you don't have to worry about which one's more highly substituted. In terms of stereoselectivity, for the formation of the epoxide, that would be a syn, right? That oxygen has to be bound to the same side because you're going to form that tight three-membered ring. If you follow that epoxide up with an acid, the stereoselectivity is now the anti-addition, right? You've got that cyclic intermediate, which means that the only way for that nucleophile to attack is from the opposite side. But then if we use the osmium oxide or the manganese oxide, that's when we would get the syn addition.